everybody, how's it going today? This will be the last video in our gases unit, and we're going to be focusing a bit more on concepts in this one than on the math itself. We'll be talking about effusion and diffusion to finish out the unit. To start out, we'll need to define the terms effusion and diffusion. Then we'll look at the role size plays in the process of diffusion, and lastly, we'll learn and apply the basics of Graham's law. When we defined what a gas was way back at the start of the year, we said that a gas has no definite shape or volume. It fills the entirety of whatever container it is in. If we think about a bottle of perfume, when we open the bottle and the gas begins to come out, that gas will take on the entire volume of a room, no matter how large that room is. The actual process of gas leaving the bottle, in this case, is called effusion. And diffusion is the process by which a gas escapes through a hole in a container of gas. Effusion is usually referring specifically to small holes, and a lot of factors go into how fast a gas's rate of fusion will be. Unlike anything we've covered so far, one of those factors is related to the molar mass of the gas involved. Now, before we look at the math behind effusion, let's talk about its counterpart in our perfume example, diffusion. After the perfume leaves the bottle, it begins to spread throughout the entire room. Now, the farther we get away from the bottle, the fewer perfume molecules will be present, as most of the gas is still in the bottle or coming out, and the gas coming out has not had time to travel very far. If we close the bottle and wait for a long enough period of time, the gas will spread out fairly evenly throughout the entire room. This is the process of diffusion. More generally, diffusion is the tendency of molecules or ions to move toward areas of low concentrations. You probably talked about this concept during biology, when looking at osmosis and hypotonic versus hypertonic solutions. Like effusion, diffusion rate is also related to the molar mass of the gas particles present, meaning some gases will diffuse faster than others. The rates of both effusion and diffusion of a gas are inversely proportional to the square root of its molar mass. If you would prefer that to be translated into English, it basically means that as the square root of the molar mass of a gas goes down, the rate of effusion or diffusion goes up. This is called Graham's law of effusion, though it applies to both effusion and diffusion. Mathematically, it is represented by the formula shown here, which is that the rate of A divided by the rate of B equals the square root of the molar mass of B divided by the square root of the molar mass of A. Notice that A is on top on the left side, but on the bottom on the right side, reflecting the inverse relationship here. Let's see an example of how this looks in practice. So this question asks, how much faster will helium diffuse out of a container than nitrogen? It tells us that helium's chemical formula is He and nitrogen's is N2. So nitrogen is diatomic and helium is single. So in order to do this, first we're going to need the molar mass. Helium's molar mass is 4 grams per mole, and nitrogen N2, each one has 14 times 2 equals 28 grams per mole. So all we need to do is go rate of He divided by rate of N2, I guess, equals the square root of the molar mass of B, in this case that's nitrogen, so 28 divided by the square root of 4, which is helium's molar mass. And when we solve this out, we're going to end up getting about 2.7. So what this actually tells us is that the rate of helium divided by the rate of nitrogen is 2.7, or that helium's effusion rate is going to be about 2.7 times faster than nitrogen. Now, if all of that math stuff has you reeling and panicked, don't worry. It's very rare that you actually need to compare the rates of effusion or diffusion in two different gases, and all it really tells you is how much faster one is than the other. Calculating the actual rate of diffusion or effusion for a single gas, however, is incredibly difficult. The rates are dependent on a variety of factors, including pressure, volume, temperature, the composition of the air in the larger container, the volume of the larger container, and the amount of gas present in the smaller container. Effectively, the important takeaway from all of this is really that the rate of diffusion and effusion increases as molar mass decreases. The heavier a particle of gas, the slower it will escape and spread out. Let's review. Effusion is the process by which a gas escapes a container through a small hole. Diffusion is the tendency of a molecule or ion to move toward an area of lower concentration, or basically the tendency of a substance to spread out evenly. Graham's law states that the rate of effusion or diffusion for a gas is inversely proportional to the square root of the molar mass of that gas. That is basically fancy science speak for smaller molecules escape and spread out faster than big ones. That's all for today, and that's the end of our gas unit. Thanks for watching, and I'll see you next time.